Good morning, everyone. I'm Chitra Babu, the Department of Computer Science and Engineering at SSN College of Engineering, Chennai. So I'm very privileged to introduce the keynote speaker of this session, Dr. Geetha Manjunath, CEO and CTO of NIRAMAI Health Analytics. She is the founder, CEO, and CTO of NIRAMAI Health Analytics and has led the company to develop a breakthrough AI solution for detecting early stage breast cancer in a non-invasive radiation-free manner. She holds a PhD from Indian Institute of Science and Management Education from Kellogg's, Chicago. She comes with over 25 years of experience in IT innovation. She has proposed and led multiple AI projects at Xerox Research and Hewlett Packard India. Before starting NIRAMAI, Geetha was Lab Director for Data Analytics Research at Xerox India. Geetha has received many international and national recognition for her innovation and entrepreneurial work, including CSI Gold Medal and BIROG Winner Award 2018, and is also on the Forbes list of Top 20 Self-Made Women 2020. She has several more accolades. Geetha is also an inventor of 20 US patents and more in the pipeline. And we are very glad to have her as our first keynote speaker. Over to Geetha Manjunath, and she'll be talking on the topic innovative screening solutions for breast cancer using AI. Please welcome her.
Yeah, hi, good morning, everyone. And it's great to be here. Thank you, Dr. Upita and Karthik, for inviting me here. And it was interesting to hear from PK and Arpita about the intent of this conference to determine what are the different types of career options that you have. So hopefully at the end of the talk, you will also consider entrepreneurship. And trust me, it's a very, very interesting, challenging, adventurous career if you really like to solve problems. And of course, I've always been a long time corporate. So if you have any questions either on the corporate side or the startup side, happy to answer. But before that, thank you for the introduction, Dr. Chitta. As she introduced, I am the founder CEO of NIRAMAI Health Analytics, but I should sort of let you know I am actually an accidental entrepreneur. Like many of you, I have been very active in professional bodies like ACMI-W and so on. And I have been a techie and corporate like researcher, both in the corporate applied research world as well as in academia. There was a very deep institute. Can you hear me? I think suddenly I went off. Okay, maybe I'm too loud and that's why I reduced. Okay. So there was a very, very unfortunate situation that happened in my life. Basically, I lost a couple of my close family members to breast cancer. So then it was almost like a calling, and I just quit my job and started NIRAMAI 7 years ago. It was a interesting decision to make, and so what it just tells you is there are different career options, but you can follow the heart, and you really can make a career out of it, whatever you're doing. You can do well if your heart is in there. That's all I can say in a sort of short while. So, of course, all of us have seen medical images. During COVID, a lot of us have seen different types, and I'm sure I'm talking to so many computer vision experts, and you would have seen thousands and millions of these, right? And when we talk about AI and machine learning, particularly AI and machine learning applications in healthcare, the primary area where this is really, really useful is in radiology, right? And radiology and AI, and there are like tons of data sets available of chest X-rays, with COVID labels, or mammography images with labels and so on and so forth. But what it has been found to help in a real setting, so basically it helps in improving productivity of the radiologist, which is obvious, and the way it does is obviously it can be a simple assistant, what we call as computer-aided analysis with assistive technologies or automated technologies. So there are different ways of using the AI itself in collaboration with the doctor. First and foremost, it has been proven to actually reduce the number of missed diagnoses. We're talking about different types of applications and benefits that AI in medical imaging can give. Oh my God, this is getting crazy. I didn't know this was open. Okay, so I'll skip this. Let's get to the real one. The main thing that I'm very excited about, especially in the last few years, is when, as a technical person or a research person or a technologist, right, you see that technology is making a difference on the life, and somebody calls you and said, without this AI stuff, no, I won't have detected my cancer. Trust me, it's the most beautiful experience you get, right? You save a life really with an AIML, and that's what have been making me live every day in the last few years. Of course, I have worked on hundreds of projects before. Obviously, being head of AI for Xerox, being a techie, I was part of each one of those projects as well to some extent. But this is unbeatable. The kind of mental satisfaction you get, right? So what this basically means is that how AI can be used to bridge the gap between the haves and the have-nots, the developed and the developing countries, right? And the rural and the urban ecosystem. How many of you remember the stage 2 or COVID, right? Where if you've looked at the TV and all of those, you will know that how the rural ecosystem was really suffering, right? There were many people waiting on the road to get into the ICU. There were so many, oxygen concentrators made overnight. There were so many smaller startups and so on building these oxygen concentrators so that we can keep people breathing. And this was because there's a severe shortage in infrastructure in the rural areas. And there's pretty much good ones in urban, but everyone flocks to this place. So this gets very, very, hard to handle from the scale standpoint. So when you use AI, and this is my premise to everyone, and of course I don't need to say too much to this audience, but it's important to take this message to everyone outside who are not really exposed to AI, right? That you can actually bridge this gap. How? In the rural areas, you can actually have automated AI bots, which is determining the priority, determining the risk, and then identifying the people who need to be brought from the rural areas to the hospitals immediately. What you heard, like at the right time, the right people, and all of that, right? And that's really possible if your AI models is working and is able to work on real field conditions at the highest level of sensitivity. That is, you're able to detect any small abnormality and then bring them for a full detail. So imagine there's no doctor. Can you make a decision? So this is possible, right? The second thing is, of course, even in an urban setting, because every doctor doesn't even have time to have tea. They're super busy, right? And so for these people, the AI bots can be used to filter out people who are seemingly normal and mostly normal, and then you can actually make the assistant do the job for it, right? And of course, this is, I'm sure, is something that you would have written in the first paragraph or if you've actually published, but I'm saying this is real, right? And how do we make this real is my story I'm going to talk about. So as was introduced, we started looking at breast cancer as a problem that we want to solve because, of course, I had my own personal story, but it also is an important problem to be solved in the world today because it is the top cancer that is killing 684,000 women every year. This turns out to be 2,000 women dying every day unnecessarily. All of them, or at least most of them, can be saved if they were detected early. The only reason we are losing them is because we're detecting in stage 2, 3, 4, whatever, not stage 0, stage 1. And it is one of the most curable of all the cancers. And we all know if you want to detect proactively, you have to do these tests sort of regularly. So if you look at what kind of tests are available, okay, these are some more available today. Mammography is the default standard, and it is extremely expensive, and there are certain other difficulties of that. But the hand examination, which is called clinical-based examination, is the default standard in by the government of India or many other governments like India. And this obviously can detect only big lumps and so on and so forth, so it only can detect stage 2 and above. So 98% of people are detecting their cancer by hand, accidentally, and then coming to the hospital for further diagnosis to see whether that lump is a cancer or not, and so on and so forth, which reduces the mortality rate to 50%. Every alternate lady detected with breast cancer is dying. Now, furthermore, when you sort of double click on it, there is also access issue because of the cost of the machine itself is 80 lakh rupees, or a real good mammography is 2.5 crores. How many diagnostic centers in India today can afford even an 80 lakh machine to be bought? And how many people are actually doing regular screening? So then what happens is that they're not able to, what they call as return on investment is low, so they will actually charge more, and so it's a 4,000 rupees per test, and how many will actually pay 4,000 every year, even because all of us will feel we won't get cancer, so why do I have to simply waste my 4,000 every year to do the screening? So that's not happening, and so it becomes a negative circle. And also, in order to do the analysis, you need good doctors. There are only 18,000 radiologists, and so that's where we all have the job. Like, how can we make the radiologists more scalable and feasible? There's also this other issue of mammography, because mammography is basically X-ray of the breast, just like chest X-rays and so on. So if there is somebody who has what's called as dense breast, which has lot more fibroglandular tissue, then the whole breast appears white, and how do you find white on a white? And so that actually reduces the accuracy. And so I may be sounding more like a doctor, but that's what I've been reading in the last 5 to 6 years, by the way, right? So, but this is a big problem, and this is something even FDA has realized and said that even the current methodologies are not sufficient. Go and do an MRI. MRI is 20,000 rupees. No way it can be a preventive screening. So it gets getting into a further difficulty of saving these lives. So what we did was, when I thought we have to solve this problem, I said, okay, why use X-ray? Because X-ray obviously increases the risk to cancer. So why do you want to do it every year and go on increasing the cancer risk for a person whom you want to save them from cancer? So we said, okay, is there any other modality that we can use to detect a similar abnormality? Of course, we looked up. There were a bunch of people, even in 1980s, who had said that, oh, they have used a thermal camera, and look, they were able to find some cancer people and so on. So we said, okay, there seems to be something there. So started a project to get, take, because there's no data set when we're discussing with, some of the frontliners here, so that there's no data set available which you can download and start experimenting. So I asked one of my doctors whom I was collaborating with for some, can I take a thermal image of a person who's probably a cancer patient? He said, yeah, sure, let's do for 2 people who's going for surgery tomorrow. And incidentally, we had a multispectral camera, so we took sort of in all the spectrum, and then we did see that there was some real signal that was coming in, discriminable signal that was coming in the infrared image. Having said that, right, the kind of image you get is, I know it's looking very different to how it looks on my laptop, but the center one is the image that you get, right? And it's basically a heat map of the temperature on the skin. So basically, like heat map, like any physics heat map, I'm saying, not the thermal kind of heat map. So basically, every point color represents a temperature value and depends on how your max and min is to actually have the focus and so on and so forth. So what we ended up doing is, obviously, this is a place where we can possibly use a pattern-based analysis and so on and so forth. And so we developed machine learning algorithms to analyze these thermal signatures, not thermal images, but temperature maps, to generate a report completely automatically saying whether there's an abnormality or not. And also we generated contrast enhanced images to mark the area of likely malignancy, so that the doctor can now look at the area that is, it's the same after the analysis, to say whether there's an abnormality by looking closer with, let's say, ultrasound or, of course, a biopsy. Okay, this is what we actually developed. And this was very novel because of several reasons. There's no structure in it. It's just a temperature map. So figuring out those, and for any healthcare problem, which is specifically clinically oriented, I think it's not just about statistical modeling. It's also about some kind of a domain modeling is required. There's so much sort of knowledge that the doctors have created over time, and that has to be captured in some fashion. And the third thing is there is huge bias or imbalance in the data, because thankfully, number of people who have cancer is much lower than the number of people who don't. But that's sort of not a good thing for people who are modeling, right? So how do we sort of handle this kind of 0.4% kind of imbalance, right? For in 100, you might find less than 4 actually. But that's the kind of issue we face, So that was another big issue. So several other challenges, but most important challenge is there's no data today. So we had to really start from scratch to collaborate with hospitals to take every data point that we need for building the model, starting from the 2 people that I mentioned. Of course, they were only positive patients. Then we had to get people who don't have cancer to come and take this image. That was also another humongous task. And what is not obvious is that there is no doctor today in this world who can look at a thermal image and confidently say, yes, there is cancer. There's no doctor today, right? Which means it is, of course, there are people who are guessing. Like there are about 500 thermographers who look at it, and for stage 3, stage 4, it may be obvious and they will guess it. But we are talking about lower, earlier cancers, right? So then we had to devise a way of identifying what is the ground truth for this, right? Because obviously this person has cancer, we know, but how do we know? We know because we are doing several other tests like MRI, mammography, ultrasound, and then tissue test is being done. So, I don't know, maybe it's the necessity aspect of it. I said, okay, let's have a collaboration where we will do this test for everyone, and the same person goes through and does mammography, ultrasound, and biopsy for positive patients, and then we take that data to train the model. So it was a very, very detailed effort to actually even build the first model, using valid data, valid labels, I would say. So, and we do have a test now, which has wonderful features, right? First and foremost, yes, it is very accurate. I'm going to share the sensitivity specificities shortly. We are able to detect much before a hand can detect. The smallest one where we know the size is 4 millimeters. I have 2 minutes more. Okay, sorry. Oh, sure. Yes, I'm going to share about it, but if it makes you happy, we have 600,000 images right now that we have collected on our own. Yeah. And we are able to detect 4 millimeter lesions, while hand can detect 25 millimeters. So it's 5 times smaller. And it's completely non-contact, non-invasive. And I'm going to show a small image of that. No radiation. We are just measuring temperature. How can we use just temperature? Yes, because when there's a cancer cell, there is higher mitotic activity. Of course, the science behind it, the medical science behind it is also important, right? There is higher multiplication of cell, which results in additional glucose use and OTP, ATP, they say, and then there is an increase in energy that's happening, which gets transmitted to the skin. There's also higher vascularity. So we started missing cancers which are very deep. So because the heat did not travel to the skin. So we started modeling the blood vessel structure using the thermal signature. And so with that, we are able to detect, because whenever the cell is multiplying, there is higher food that it requires. So it comes through the blood flow, and the velocity of the blood flow increases. And so we were able to model those vascular structures as well. So we can do that without radiation and without any change in the density or age, because there are about 30% of cancers under 45 years. And so we need to sort of catch everyone because we can't afford to lose younger women. Definitely not older also, but definitely not younger, right? So, and most importantly, we made the whole thing, 1/10 the cost of what was existing there. And in many cases, we are able to do it free of cost as well. And last but the best is also the experience, right? Instead of sort of removing clothes in front of somebody else and then being touched and so on, we made it completely privacy aware, where she sits in front of the device like a passport photography session, but there is no photographer, right? So you go inside, close the door, and then remove the clothes and sit in front of the device for about 10 minutes, and you come out, the report will be ready, obviously, thanks to the analysis. So our mantra is no touch, no see, no pain, no radiation, which is actually something that is attracting so many ladies to do it. It's really about enabling everyone to take this test and without hesitation, without worry, right? And that is what it is able to do. So here is sort of closing the door and sitting in front of the device and just rotating to get all the views. Of course, it has resulted in a lot of awards, and thanks. I also met Bill Gates. If it encourages, and even I met Sundar Pichai. I've met. I was actually in September invited to present this technology in United Nations General Assembly in New York, sitting next to the president of UN. It was like amazing. 2 weeks ago, I met the president of India, which is also a super experience, and she happens to be from Odisha. So several things have come forward with this because thanks to AI. Okay, all good. So let's get into the whole thing, right? Hopefully, now may have created the enough enthusiasm and eagerness to see what's happening. Let me sort of put out like a disclaimer, right? It's really not about the specific algorithm, because what I realized is that definitely algorithms are important, getting the best accuracy is important. But how do we make it work on the ground is the most important thing. And doing it in a way you will not hurt the person. But here you go. So the temperature is basically, of course, thermography is basically measuring the temperature on the skin. So you measure it, and every point here, is a, so every temperature gets a color, right? The rainbow palette and so on. So you see it this way. So this is good. But what happens from a manual interpretation standpoint? I think I briefly mentioned, these are two same people. There's 39 degrees as max, and next is 36 degrees. So what these thermographers used to do is like, what is the best max I have to use, mainly have to do, so that I can start seeing some patterns, which is the right max, which is the right range that you have to use, what is the cutoff temperature above which something is hot. So these are all very, very arbitrary in nature, right? Visual in nature. So for example, there is this cancer here, but you can completely miss it. Whereas in this view, you can get it. So all this is super complex because we are looking at 400,000 temperature points. And so what we did was we made sure that the 5 views are taken, kind of 180 degrees view, uploaded into our AI set of models. So it's basically thermalytics.com. Whoever has login password can go in, upload, and click, the result comes out. So you have to make it so simple for the end user. End user now is a doctor, and doctors are the least tech savvy, trust me, right? Anything you have to do it and say, just do one click and you should get it. So we actually train technicians to just even upload, take the images and so on. So you upload. There's several, about 20 plus AI algorithms running behind. Many of them we kind of had to do because we are looking at real data. First and foremost is the well-known phrase, no garbage in, garbage out. So you have to make sure, is it garbage? So when a technician is trained and she uploads, so we have to do a lot of quality checks on the image, whether it is of the right views are taken and so on. And even before that, the protocol for capturing the image itself, right? how to capture thermal image. There's no one else in India who is doing it, right? So, but of course, we looked at literature and then figured out what is the easiest way. Somebody said, put them in a chamber, temperature controlled chamber and so on and so forth. But that's not going to work in a field if you want to do it. So we came up with a protocol where we blow cool air for about 5 minutes. So there's a contrast enhanced, and then, we start taking it. And of course, there are AI models to check whether when she's ready for taking the image and so on and so forth. And I really don't know how much time I have, but we also have to make it more explainable. So, yeah, 15 minutes. Okay, good. So we when you go to a doctor and say, yeah, here is a person who is positive, said, why should I trust you? Why should I trust this AI model? I don't even know, like, there's nobody who's using thermal, so in my network, and how do I know that you're right, right? So then we have to say, okay, go ahead, verify it. Here is the marking. I showed you the marking in one of the images. Go do an ultrasound, you'll find it. So we had to really create that trust by showing real facts on the ground so that, they can validate it or in their own methodology, using their own methodology. And once we started creating more and more such example use cases, and obviously nothing less than peer-reviewed publications. So publications in clinical journals and conferences made it happen. But coming to the point of explainability, we actually also were able to say, are we saying this is abnormal based on the cell division that's happening, vascular abnormality, milk duct issues? So we were able to go into the semantics and also give different scores for that. So the quality checks obviously is a simpler problem because it's more like an anomaly detection issue. You can also say it's a class 1 versus class 2. So we use ResNet, simple ResNet. Obviously, the loss function had to be completely determined by us. And then we did get excellent tagging accuracy, determining the view. Then also looking at the image and segmenting the right piece is important because we want young technicians to be able to do this. So we got excellent dice index, even above the inter-observer dice coefficient you will see, like with some technicians. Next important thing that we did was also to identify what is a hotspot versus not, right? So we actually came up with a decision. It's a machine learning, but it's a decision tree, I would say, or decision function rather, where we are able to identify, more like it's a function of a histogram, where you identify whether what is the temperature above which for this person, which is abnormal or not. So that was another interesting pattern that we had to come up with. And then also we have new algorithms to extract blood vessel structure. So once we start looking at blood vessel structure, which are differential in nature, so what you're seeing is that there are lots of blood vessels on the right side and not in the left side. Obviously, she has blood vessels on the left side, but if you look at it from a differential perspective, differential velocity perspective, so we were able to extract. Then you start modeling the network, right? So the point is, it's not exactly which algorithm, like what are the steps you will follow so that you can get there. So how do you model your problem in the form of known algorithms, let's say, or you can, of course, you also have to innovate on the algorithm space, but it's more about how do you model the problem in a way that will work, right? So there were many the whole structure had to be built from the beginning. So we used simple image processing sometimes, deep learning sometimes, of course, simple traditional machine learning models sometimes, depending on the amount of data we had, amount of confidence in the labeling we had, and so on. So we ended up getting actually better accuracy than mammography also. So you see one person there, which has equivocal sort of left and right dense tissue in X-ray, but we're able to identify that cancer. And this is something that every doctor really wants to see. Can I detect some people whom I've not been able to detect with my regular technology? So we also sort of worked with doctors to figure out what is the kind of report they want to see. So we actually had scores indicating the level of abnormality. We are all used to a blood report where they say this is the right range, and if you are not in this range, there is abnormality. So we need to sort of bring our thought process or our output into that format, because that is when the doctors will feel comfortable. That is when the patients will feel comfortable as well. So all this has actually resulted in 33 granted patents. And again, if any of you want to learn about how to patent and it's not about making money with patent. It's about doing your work without somebody else's objection. That's what mostly it is. But yeah, we have 11 granted patents in the US and 13 in India and others in Japan, China, Singapore, Canada, Europe. And we also had to publish in clinical and also, of course, technical journals. Maybe I put only the clinical piece here to show that, of course, the algorithms were unique, but also the results that were gotten were compared with the final answer key, which is the tissue test. So every person comes in, take this test, and the same person goes through all the rest of the tests, including biopsy. And at the end of the whole question paper, about 300 patients, 600 patients, depends on the sample size that's relevant to the question you're asking, then external person will come in and say whether these two matched or not. Trust me, when the test is being done, nobody knows the answer. Okay, so it's not the kind of testing we do in the lab where you have fully labeled data set and you'll do 80-20 rule and you'll show 99% accuracy in the 20. It's great to start with, but it's definitely not what will run on the ground. Sorry if I'm hurting some of you, but that's reality, right? That is the fun of working on real data. And yes, what was surprising, even in such a setting, we were able to get 100% asymptomatic sensitivity. That means we did not miss any cancer that was found by either a mammogram or an ultrasound or and confirmed with biopsy. And of course, you can't have 0 false negatives, false positives. So it turned out to be 8% false positive rate, which is pretty okay. What we are saying is 8% of people may need additional tests and they may say, no, there is no cancer. And what was also interesting is when we compared this with mammography, we ended up getting much higher sensitivity than mammography as well. So a lot more women who were not able to detect their dense breasts were able to detect it also. So this I thought would be interesting for those of you who are thinking about machine learning in medical imaging. So there is, of course, a problem creation. You have to determine what is the problem you want to solve. It's not just like breast cancer screening is a problem, but what would be the sub-problems that may arise there? And for each of it, is there a model that we are thinking about? And making sure that you don't have sort of bias in the data that is that you're collecting or you're given, and making sure that there is veracity in the labeling is also very, very important. And like I briefly mentioned, lab and in-house testing is great. That's only a beginning, right? But maybe that's an ending for some of the publications, but that's the beginning for any field deployment. And after that, you have to give the tool in the hands of a doctor, in the hands of the end technicians, and then measure the efficacy. There again, you can do what's called as retrospective testing or prospective testing. But finally, there should be some clinical body, regulatory body, which will actually say, yes, this is working, right? And you can use it officially on people. So we fortunately were able to, with a lot of understanding of what needs to be done, working with mentors, working with experts in the field, able to get not just India clearance, but also in the US and Europe. We just sort of make made in India, very, very, very few made in India, AI-based medical imaging going and doing, getting used in other parts of the world. So far, about 170,000 women have benefited from this test on the ground. We've detected thousands of cancers which wouldn't have detected earlier. And we're commercial in about 8 countries, India, Kenya, Turkey, Philippines, Sweden, Dubai, Abu Dhabi, Bulgaria, US as well, right? Several other hospitals around you are using it as well. And a lot of corporate camps that we have conducted. Of course, we have benefited thousands of rural people where we did it free of cost. We also have we kind of incorporated into a small tempo traveler so that it can go into the real corners of India. And we have very top names here at CG, Apollo, and Narayana Hridayalaya, all of them using it, as well as, Googles of the world, hide meeting control so that you can see. Yeah, who can, who have already started providing this to their employees. That's, and so many women who didn't know that they had issues got, benefited. I think I'll skip these things for the want of time. But basically, we also made it very flexible to use, either in a hospital or in villages, in a district hospitals or any other place. Skip that. You have to make it. I thought I'll make it interesting for explainability, but maybe I'll skip it. So basically, I'll kind of end with this slide, where open for collaboration. I know there are a lot of academic institutions here and industrial sort of R&Ds, because I feel we've just scratched the tip of the iceberg kind of a thing, right? There's a lot more we can do. I feel that we have probably stumbled upon a new method of detecting abnormalities in the body. We are already seeing it happening with some Bill and Melinda Gates Foundation grant. We were able to figure out skin abnormalities with it very accurately. In Ghana, we've started seeing some benefit in head and neck cancer, some benefit in diabetic foot already detection. And I'm sure there are tons of other diseases that we will be able to detect without touching the person, without seeing the person. And I feel there can be an ATM. You can walk in, close the door, and come out, and you're like a blood report. Where is the problem, and you can go if there is any problem. So I'm open to collaboration. Definitely questions on any of these. Happy to take.
Thank you, Geetha, for that very informative and wonderful talk. Audience, do you have questions?
Like, could you say, like, among the ones that are turned positive, like what fraction are actually, they have cancer?
Yeah. So basically, among the ones who are turned positive, how many of them? That's it's called positive predictive value, right? So it depends on how many. It's right. It depends on how many. Are you doing it in a hospital setting where people have walked in with a symptom? So then obviously our positive predictive value is PPV is much higher. So that if maybe even for example 20% false positive rate, 20% PPV is considered great, because you're leaving out 80% of people that need not come to the hospital. So I had this funnel which actually answers your question. For example, in Punjab, we did about 15,000 people screened in villages and all. 300 of them had to be brought to the hospital, right? In that, some of them are still going through the follow-up diagnostics. Some people are saying, kuch nahi hai, ghar mein baitha hai. All that is happening. But already 10% of them have been confirmed malignant with biopsy and started treating. So 30 people already see just with one device moving around to different places. So if you see what is the equivalent number with our previously used method, with the clinical based examination, it is 1/4. The same 25,000 women screened, less than 10 people detected with cancer. Obviously, we have not created cancer in any of them. It's just they were running around, right? And that is what kind of has benefited this. Yeah.
So if I'm understanding this right, this shows that it's better detection in asymptomatic people. That would be the inference.
Yeah, definitely better detection is asymptomatic. Symptomatic also we detect. But yes, we focus on asymptomatic because symptoms, it's important that they better get to it, but they usually go because they will start seeing something abnormal. But it's important to detect before stage 2 if you want to save them for 50 years after that. Otherwise, we lose them within 5 years. Yeah.
Thank you so much. This is great.
Yeah, you have a question here. Yeah, say your name and yeah.
So I am Prerna Mukherjee from JNU. I'm a faculty at JNU. So ma'am, I have a few questions. You mentioned the false positive rate. What is the false negative rate?
So you have many statisticians here. False negative rate is 100 minus sensitivity. When I say sensitivity is 100%, it is actually 0 right now.
Okay. And what's the frequency of getting this test done? Like for mammograms, there is some frequency, right?
Yeah, that's also interesting. Many of the doctors and patients kind of ask this. Okay, I'll give you the actual answer, but then because we are all innovators, so basically it's like you can never say when cancer will appear where. Like it's mostly a guesswork, right? So just like mammography is done annually, we would recommend do this annually. But we went one step further. We give scores. Just like a diabetic, you're doing a glucometer test or something, right? So imagine there's a litmus paper, you dip into the blood and it'll give you some color shade and you have to guess whether it's, that's what thermography is now. But when we put in a number, like a glucometer says 100 or 300 or 90, right? You know whether it is, what level, how close you are to the boundary. So let's say you're 150, then you need to sort of reduce sugar and do the test more often. Same way, when we give a scoring, if the scoring for the person is close to 0.5, it's a probability value. So anything above 0.5 has a probability of being malignant. So 0.4, then we say, why don't you do it in 6 months? If it's 0.3 or 0, then she can even do it for 3 years, after 3 years. It's amount of confidence you have on the thing, but generally we say once a year or once in 2 years.
And does the thermogram have any possible side effects over the long run?
Absolutely no. It is, see, all of us have gone through thank you for asking this, right? So we have this sort of thermal gun, infrared gun. It's exactly that. It is not throwing any energy on the person, because our body is a source of energy. Like, we are always 37 degrees Celsius, irrespective of whether we are in Kashmir or, here, right? So that is what it is measuring. It's just measuring the radiation that is coming in from our own body. So absolutely no side effects. Yes, we blow cool air for 10 minutes, but it's only 21 degrees, I think. अगर chill होगा तो enjoy the chill. That's all.
So are you planning to also extrapolate this to other sorts of cancer?
Yes, definitely. That's the previous slide
And
talked
does
about.
it detect metastasis?
Yeah. So, okay, what it doesn't detect is if something is wrong inside the brain or lungs or, blood or something, that it can't detect, right? Because there's no soft tissue or you can't model the thermal signature. So, so that is an issue.
Thank you.
But yeah, I think we are running out of time. I see the signal. So
No, we can have a couple of more questions.
yeah, okay.
So wonderful talk, Geetha.
Thank you.
I actually follow your work a lot. I'm also a budding entrepreneur.
Your
I'm,
name,
very naive.
Do you want to tell your name?
So yeah, my name is Diksha Bhartiya. My startup is called Genomic Solutions. We work on genome informatics solutions for genome testing. Since breast cancer is an inherited disorder, and I just wanted to know that when you have developed this model, have you also incorporated the data of the family history, the patient demography, and all those features which might also have an important, importance in this particular thing?
Yeah, that's a good question. So actually, I didn't go into the sort of the report format a bit, but basically we give different scores. There is it because of inflammation? Is it because of vascularity? Is it because of milk duct closure? We also have an ensemble score. To this audience, I don't have to define ensemble. Awesome. But usually for the doctors community, ensemble is a joint, a combo score, all that I keep telling. Anyway, so the ensemble score actually uses the other patient demography information, because we are AI, so we better take whatever information is available about the patient. Right now, I don't have genetic data. Obviously, it's something that we have to incorporate, because not many people in India do genetic testing. The BRCA positive one, you may be aware, BRCA1,
So
BRCA2.
because we are doing that, so I was thinking maybe
Yeah,
this
I mean,
venture of a
definitely we can,
collaboration.
if any of the people have done genetic testing, we can incorporate that. Right now, we take family cancer history, age, menopausal, all of those sort of, well-known risk factors are taken into account to generate a final ensemble score.
And it's I have another question. So for the patient that whom you are who's going for this thermal screening, are you also advising the other, because this runs in families?
Sorry, I missed the last part.
So basically, the patient who's going for thermal screening and you identify some measure and you score the person to be breast cancer positive. So do you also sort of advise them for screening for other patients, because other family members, because this definitely runs in families, so there might be huge possibility.
Yeah, usually this happens by default. So they say, it's more like, I like this experience. First, she will actually bring her mother. Then the mother will say, this is very good, you have to do it. So it's more in terms of the experience which enables it, not the scare of the risk, actually. But yes, we work with doctors to say that whenever you're treating a cancer patient, get all the family members do this. But it's more evangelization activity.
Yeah. And because it will be very interesting to see that what kind of thermal pattern comes with what kind of mutation.
Right.
And correlate both of them.
Yeah. I don't have that information right now, but it'll be good if you are able to get it. Yeah.
Thank you.
Thank
Thank
you.
you for that.
There's more question at the back. Really, if there's no time, I can take it on lunchtime. Yeah.
Okay. PK faculty at IIIT
Yes, of
Hyderabad.
course. You're
Um,
wonderful on the stage. Yeah.
Thank you. So I have two questions, one technical and one non-technical. The first technical question is, so what are the thoughts around privacy for this? Meaning I'm more so the algorithmic privacy, not necessarily the physical world privacy. My second question is, you told about your success stories. Can you tell one or two challenges and stories that did not work out the way you thought it will work out?
Sure, thank you. So regarding the data privacy, obviously when we actually start asking for regulatory clearance outside India, it becomes more, now India is also going towards that. So what we consciously did was initially we didn't even take the name and phone number or email ID of the person, so that way, we are not even keeping any private data, because I just wanted to be clean about any of the sort of the guidelines that are there, and we don't want those to be affecting. So we were only giving patient ID, AS001 and all that. Then people started saying, I don't know whether it's mine or my mother's. Oh, I have to look at the age and figure out if it's my report, or because they don't know the patient ID. So then we actually do consent forms saying that I will take your email ID password only for sending you the report and making sure your report gets. So that's the only private information we're taking. But as far as that is only at the sort of the client tool end. But as far as the cloud is concerned, to do the analysis, it's completely anonymous. I showed so many images and we don't even know whose images it is, right? Even the lady will not be able to recognize her own image in many cases, right? So it's already anonymized data. Right, so that is what is giving us a lot of power. For example, when we work with Dubai, Abu Dhabi, they're super conscious about the privacy regulations in the area. So we worked with them to develop a client tool where they'll take all the inputs of the name, phone number, and then map it to a number, and they'll give the anonymized number to us. We also don't know who the patient is when it comes to the cloud, and we have a reverse mapping that is happening on the tool. So we had to do some of these things, and cloud is available in different zones, like in AWS. We right now work on AWS, so that way we run in the same country zone, so that they don't feel that intercountry transfer is happening. So some of this, so we are GDPR compliant, HIPAA also compliant. So these things are necessary. To your second question, I think for any entrepreneurship, right, there are a couple of things. So one is your belief in the idea that it will work, and it should not be a dumb belief or blind belief, right? As again, all of us being scientists, we have to prove to ourselves that it is the right idea. I mean, it's very hard because you love your idea, you love your baby, you always think it's right. But you sit on the other side and say, okay, if this is happening, then I need to fix it, right? Or is this result that you're getting correct or not? So being a critical judge of your own results is very, very important. So once you have that, you have a strong belief in the idea, you have to hold that belief irrespective of what others say. I think it's so important. First few years, we were only getting a no, 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 no. I mean, I've never read this in my book, my MBBS degree. Why should I do? Boss, I started using Dr. Geetha a lot more. I was not, though I have a PhD, I was not using the word doctor, but I started using that more because then you get some recognition in front of the doctors. They agree to talk to you. I mean, trust me, it's a different community. It's different community. Are there any doctors here? They're like, everyone is dirt. There are many doctors who are beautiful, who are very, very open, but many of them, because obviously they're saving lives, they're God, definitely, I honor them. But so this kind of a thing, right? You're not even from any of the medical community. How can you tell me what I have to do, to treat me? So these things, I think those are the main challenges. And I didn't want to refute them. I said, yes, I am not from your community, but I want to work with you. Tell me, what should I do? What should I prove to you so that you will accept this and start using it? I think the first few years of rejection is the main thing. So I went back and said, okay, they want me to publish in Lancet Oncology. Somebody, trust me, in India, there will be very few doctors who are published in Lancet Oncology. Lancet is like ASPLOS or those kind of things, like literally huge, merit for publishing. So some doctors threw at me like this, you have to publish in Lancet Oncology. I said, okay, you have to make it a policy in India. I mean, I'm a small, person sitting in. How can I change the policy? But I said, okay, this is what? Okay, I'll do it. Let me figure out how to do it. I think this kind of saying, okay, this is what will make it work, and I have to find a way of doing it. And finally, in 2023, January, we got a Lancet Oncology paper. That was literally for me, right? And it's amazing. Now I know what to put in front of the doctors, right? And probably that slide was purely made for doctors. I should have made a new one for you. But I put all those logos which doctors appreciate. And there is a conference that happens in San Antonio, Texas, just breast cancer symposium. It's called San Antonio Breast Cancer Symposium. About 7,000 oncologists come there. Everyone from all over the world come there. It's an amazing conference. The person who invented chemotherapy comes in there. He's like pura white daddy and all. It's super, okay? And every year, last 5 years, we've had a poster. I haven't made it to the paper yet, but poster there every day. And this one is absolutely a record from any Indian working in breast cancer. These kind of things I go and tell the doctor, right? Some of them say, okay, fine, there is something in it. It's like that Indian mentality is like that. Firangi log haan bol diya to ye haan. So anyway, so I had to actually also get US FDA for that reason. So these are some of the challenges. Main challenge is getting the trust of the doctors to start using it. Yeah. So maybe I will close with one last question. Yes, I keep spamming them with list of publications. Initially, I was not putting it up on our website because they were like these crazy guys who are trying to copy and claim it is same. But I have now put it up. Anyone can look at our publications, niramai.com/publications. But mostly we are focused on clinical in the last few years for the obvious reasons. Yeah, over to you, ma'am. Last.
Hi, ma'am. My name is Anisha and I postgraduated from CMI.
Okay, nice.
So, first of all, this is an amazing talk, like very
Thank you.
interesting. So, I had one small technical question.
Sure.
So, you mentioned that the temperature range for hotspot detection changes from patient to patient. So, my question was that change or that optimal value, are you obtaining it like before training the model, or is it like chosen on the go when a patient is diagnosed using the tool?
We have a model which predicts, which takes the temperature distribution and predicts that threshold.
Okay.
And that is obviously improvising every time. Yeah. And we try to predict only those where there is either a benign or malignant case. Benign is like looking like cancer, but it's not. So those also we'll take, and then we have trained that model. And there are several things when you actually put it up, you can't learn on the go. These are some regulations. But yeah, if any, hopefully, but thanks for that question, and it's a simple answer. But hopefully this has made at least a few of you want to, feel more, you already wanted to do some startup, but maybe you got more courage to do it. But one line about that is like, of course, I didn't know anything about finance, stock options, and I'm now running a company with 100 people right now, right? And it's really what takes you is the goal that you want to achieve. And if that goal is really beyond yourself, like basically you're helping people and so on, you'll really find a lot of people helping you, learn things which you don't know, go towards that direction. So all the best, and thank you so much for listening.
Thank you very much, Dr. Geetha, for the excellent talk, and thanks for all the questions and making it interactive. So there's a lot of, it's very inspiring to learn about you. Thank you for your time.